rainbow.
Yes, it's very beautiful. In fact, the legends of many cultures see the rainbow as a kind of bridge between heaven and earth.
Really? Well, that's an interesting idea.
But science has figured out the secret of rainbows. I can reproduce a rainbow for you using a triangular prism.
Oh, how does that happen?
Well, the same phenomenon takes place in both cases. Refraction of light. In this lesson, you will learn about dispersion and scattering of light. At the end of this lesson, you will be able to identify the general terms associated with the triangular glass prism, demonstrate refraction of light through a triangular glass prism, demonstrate the dispersion of white light by a glass prism, explain atmospheric refraction through twinkling of stars, apparent sunrise and sunset, explain through the concept of the scattering of light, the Tyndall effect, and reddening of the sun at sunrise and sunset.
You said you could show me a rainbow through a prism. What exactly is a prism? Is a triangular glass prism a special kind of a prism?
A triangular glass prism, to be specific, is a piece of glass that has 2 triangular and 3 rectangular faces. You may have studied how light refracts through a glass slab. You can think of a prism as a triangular piece of glass carved from a white-bottom glass slab. Let's see how light refracts when the glass slab is converted to a prism. Consider ABCD, the cross-section of a glass slab of a certain thickness. A ray of light is incident on the face of the slab, represented by AB. This incident ray refracts through the path shown. After refraction through the 2 surfaces, the ray emerges from the face of the slab represented by DC. The surfaces of the slab represented by AB and CD are parallel. Hence, the emergent ray is parallel to the incident ray. We truncate the surface of the slab represented by CD so that the cross-section now forms a trapezium as shown. As you can see, now the emergent ray is not parallel to the incident ray anymore. As we continue truncating the slab, the direction of the emergent ray keeps changing as shown. Finally, we get a shape with 3 rectangular surfaces and 2 triangular faces. We refer to this as a triangular prism.
Wow! I can see how the emergent ray is emerging at a different angle altogether now.
Yes, the shape of the prism impacts the way the incident ray refracts. The formation of a rainbow is a combined effect of refraction and another phenomenon called dispersion. Let's begin with refraction and review the general terms associated with the triangular glass prism. The rectangular faces in a triangular glass prism are known as refracting surfaces. The line along which the 2 refracting surfaces meet is known as the refracting edge of the prism. The angle between the 2 refracting surfaces, denoted by the capital letter A, is called the angle of the prism or the refracting angle. The base of the prism is the rectangular face of the prism that does not take part in refracting light. Consider XYZ, the cross-section of a triangular glass prism. When a light ray PQ is incident on the face XY of the prism, it refracts at the 2 refracting surfaces of this prism and follows the path PQRS as shown. Now, a quick recap of the terms associated with refraction. The ray of light that is incident on a surface is called an incident ray. Therefore, PQ is the incident ray. Q is the point of incidence. The ray that deviates at the point of incidence due to a change in the medium is the refracted ray. In this case, the refracted ray is the ray that travels inside the prism between the two refracting surfaces. Thus, QR is the refracted ray. The refracted ray again incidents on the other surface of the prism and then emerges from it into the air. This light ray emerging from the prism after refraction is called the emergent ray. Here, RS is the emergent ray. Normal is the imaginary line drawn perpendicular to the surface at the point of incidence. The angle formed between the incident ray and the normal at the point of incidence is known as the angle of incidence. Thus, here, angle I1 is the angle of incidence on the face represented by XY. Similarly, angle R2 is the angle of incidence on the face represented by XZ. The angle between the normal and the refracted ray is known as the angle of refraction. In the absence of the glass prism, the incident light ray would follow the path PQ/OQ'. Due to the prism, the light ray emerges along the path ORS. Thus, the light ray deviates from its initial path. The angle between the directions of the incident ray and that of the emergent ray is called the angle of deviation and is represented by Greek letter delta or theta d or the English letter d. Here, angle Q-OR is the angle of deviation. When the light ray PQ incidents at Q on the face XY of the cross-section XYZ of the prism, it refracts and propagates forward inside the prism. As the light ray passes from a rarer medium, which is air, to a denser medium, which is glass, it bends towards the normal. When this refracted ray incidents on the other face of the prism XZ at R, it refracts again and becomes the emergent ray RS. Here, the light ray refracts from a denser medium, which is glass, to a rarer medium, which is air. Hence, the light ray bends away from the normal. Thus, a light ray refracts twice as it propagates through a triangular glass prism. The emergent ray always propagates towards the base of the prism.
Okay, that was half the picture. What about dispersion?
To understand dispersion, let's look at some videos of our annual day celebrations.
I remember the amazing lighting. I wonder how they got those effects.
Actually, prisms were used for those effects as well. That's where dispersion of light comes in. Light rays refracted through a prism disperse and give rise to very vibrant colors.
Where do these colors come from?
You'd be surprised to know that these are all constituents of white light. When a white light ray passes through a prism, it refracts and splits into its constituent colors in the process of refracting through the prism. The splitting of white light into its constituent colors is called dispersion of light. This is how you get the rainbow effect through the prism as well. Light disperses and creates a rainbow effect when it propagates and refracts in a prism. Let's conduct an experiment to see how we can create this rainbow effect through a prism. For this experiment, we take a prism on a horizontal surface as shown. On one side of the prism, we place a source of white light. Between the light source and the prism, we place a cardboard having a pinhole. This helps in producing a very narrow light beam through it, similar to that of a ray. Finally, on the other side of the prism, we place a white paper as shown to catch the dispersed emergent beams. This white paper acts as a screen. Can you see that strip of colors? Let's check out the order in which these colors appear from bottom to top. First is violet. Second is indigo. Next is blue. Then green, yellow, orange, and lastly red. The same colors as that in a rainbow, right?
Yes, I see what you mean by creating a rainbow through a prism now.
To Iranian Muslims, even the brilliance of the colors in a rainbow is significant. For example, prominent green means abundance, red means war, and yellow brings death. Note, the order of colors in a rainbow is popularly identified using the acronym VIBGR, each letter standing for a color in order. The same order of colors is visible in a rainbow.
But a rainbow has bands of colors.
Don't worry. We can create bands too. Suppose you replace the cardboard having a small pinhole with the cardboard having a horizontal slit, that is, an extended light source. The vertical strip of colors you just saw expands to bring out bands of colors similar to a rainbow. There! Doesn't that look like a tiny rainbow?
So, it does.
Auditorium stages are also fitted with hidden rotating prisms that give exciting visual effects to support the performances on the stage. In stage lighting, several light beams are passed through rotating prisms to create spectacular effects.
But why do these colors get separated when passed through the prism?
When white light propagates through a prism, it refracts at an angle. However, the angle of refraction of each of constituent colors of light varies a little. This is because the frequency and hence the wavelength of each of the constituent colors of white light is different. This leads to a difference in the refractive index of the glass for each of the colors. The difference in refractive index leads to different angles of deviation for each of the colors when light is passed through the prism. This is how we obtain a band of different colors on the screen.
But there is no prism in the atmosphere. So where does the rainbow come from?
I was just coming to that. Let's now solve the mystery of the rainbow. As it happens, we do have something like prisms in nature. On a sunny day, when the rainfall has just stopped, some raindrops remain suspended in the air. These drops act like refracting media, like prisms, for the sunlight. When sunlight incidents on these raindrops, it gets refracted and disperses to reveal its constituent colors. Thus, you can explain the formation of a rainbow through the concept of the dispersion of light. The refraction of light leads to a number of other phenomena that you see daily. Remember the rhyme about the twinkling stars from your childhood?
Sure, I do.
Well, why do you think stars twinkle?
I'm not sure. I never really thought about it. Is refraction associated with twinkling of stars?
Definitely. The twinkling of stars can be explained through atmospheric refraction. Atmospheric refraction refers to the apparent random wavering or flickering of objects due to inconsistency in the physical conditions of the refracting media, such as air. In fact, atmospheric refraction can explain twinkling of stars as well as apparent sunrise and sunset. Let's first look at the twinkling of stars. Since our atmosphere is heterogeneous, that is, made up of many layers of various densities, the light reaching us from the sun or stars is refracted multiple times. As it crosses each medium, it refracts. Since these media or the layers of air are constantly moving, the angle of refraction of light is changing continuously. Therefore, we see the light from the stars flicker. In scientific terms, we refer to the twinkling of stars as astronomical scintillation.
That's very interesting. And what were you saying about apparent sunrise and sunset?
Well, not many of us realize this. But the fact is, we see the sunrise before the sun actually rises above the horizon. So, when we see the first rays of sunlight, we are actually witnessing an apparent sunrise. This happens because atmospheric refraction causes astronomical objects to appear higher in the sky than they really are. Similarly, sunset occurs shortly after the sun crosses the horizon.
How does this really happen?
When the sun is just below the horizon, its rays enter Earth's atmosphere and are refracted towards the Earth. The refracted rays reach us, making it appear as if the sun has already risen above the horizon. This is the apparent sunrise. The actual sunrise occurs when the sun actually crosses the horizon. Conversely, the apparent sunset occurs slightly later than the actual sunset. Since the light from the sun is already below the horizon, it refracts through the atmosphere, enabling us to see the apparent sunset even after the sun has already set. Now, another question for you. Can you tell me why the sky appears blue in color?
Well, that is the natural color of the sky, I guess.
If the natural color of sky is blue, then why does it appear red during sunrise and sunset?
I'm not sure. What's the reason behind it? Is it due to refraction of light as well?
Not quite. It's the result of scattering of light. Scattering of light is the deviation of light rays from its straight path. Almost all objects scatter light. That is, they reflect light rays incident on them. But some objects scatter light of some specific wavelengths, like the white ray of sunlight from the ventilator of your classroom or the golden hue in the forests. Light travels in a straight line as long as no object or particle obstructs its path. However, most media are heterogeneous, like our atmosphere, which is a mixture of gas molecules and other dust particles surrounding the Earth.
And as light propagates through the atmosphere, it travels in a straight path until it is obstructed by bits of dust or gas molecules, right?
You got it. Out of the 7 colors of light, blue has the shortest wavelength, and therefore experiences more scattering than other colors. Therefore, the sky appears blue to us.
Very interesting. Are there other examples that show the scattering of light?
Sure. Scattering of light gives rise to many amazing and spectacular phenomena such as Tyndall effect, reddening of the sun at sunrise and sunset.
What is the Tyndall effect?
The Tyndall effect is the scattering of light by colloidal particles. Observe this narrow beam of light. When I pass it, through this colloidal solution.
Wow! I can see the beam of light passing right through the solution.
Yes, that is the effect of the scattering of light. When the beam of light is scattered by the colloidal particles in the solution, its path is illuminated. This phenomenon of the scattering of light is called the Tyndall effect. The illuminated path of the beam is called the Tyndall beam.
Is it only in colloidal solutions that we see the Tyndall effect?
No. You can observe the same even in air laden with dust particles, like in a dusty room. The Tyndall effect can also be observed when a fine beam of light enters a room through a small hole, such as an aperture in a ventilator. This happens due to the scattering of light by particles of dust and smoke in the air. Similarly, when sunlight passes through the canopy of trees in a forest, you can see the Tyndall effect at work again. The mist in the forest contains tiny droplets of water which act as particles of colloid dispersed in air. In fact, here's an interesting incident related to the Tyndall effect. London, in the summer of 1815, frequently saw prolonged and brilliantly coloured sunsets and twilights. This was explained by the Tyndall scattering of sunlight by ash particles in the upper atmosphere. These ash particles were produced by the earlier eruption of the volcano Tambora. Now, look at this sunset. The sky has turned red.
Wow! What a lovely sight! You said that the red color of the sun at sunrise and sunset can also be explained through the scattering of light.
Yes, let me explain. As the sun begins to set, light must travel farther through the atmosphere before it gets to you. Therefore, more of the light is scattered. As less direct sunlight reaches you, the sun appears less bright. The color of the sun itself appears to change, first to orange and then to red. This is because the short wavelength blues and greens get scattered. Only the longer wavelengths are left in the direct light beam, which is what reaches your eyes. Therefore, you see longer wavelengths and the sky appears red, pink, or orange. Can you recall any application which you can relate to the scattering of light?
I think I have heard about the red color used in danger signals, but don't know whether it relates to the scattering of light.
Actually, that's a very good example. Red has a longer wavelength, and hence it is least scattered in any type of the atmospheric conditions. Due to this, the signal appears without change in color for longer distances. Therefore, it is effective to indicate the danger signal universally. This brings us to the end of this lesson on dispersion and the scattering of light. In this lesson, you have learned about refraction and dispersion of light through a triangular glass prism, formation of a rainbow, atmospheric refraction, and the scattering of light. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. The formation of a rainbow is a natural spectrum that occurs in the sky after a rain shower. This happens due to a phenomenon called the dispersion. To understand the phenomenon of dispersion, let us first understand the passage of light through a prism. A prism is made of a transparent material like glass. The prism ABC shown has two triangular faces, and there are three rectangular faces. The angle between its two refracting faces, AB and AC, is called the angle of the prism or refracting angle and is denoted by A. We can have prisms of different refracting angles. For example, an equilateral prism has a refracting angle of 60 degrees. Let us now learn about an experiment with the prism to measure the deviation produced by it. Let us fix a rectangular drawing sheet to the drawing board. Let us take the prism ABC, which we used earlier, and place it on the drawing board such that the triangular face is in contact with the drawing board. Draw the outline of the triangular face on the drawing board. Mark it as ABC such that AB and AC are its two refracting faces. Next, we remove the prism and draw normals N1 to AB. Draw line PQ such that it makes an angle of 30 degrees with normal N1. Fix two pins, P1 and P2, on line PQ. Place the prism back at its original position on the drawing board. Now, observe the images of the two pins on PQ through face AC of the prism. Place two more pins, P3 and P4, on the drawing board, such that all the four pins appear to be in a straight line. Remove the prism and pins from their positions. Draw a straight line TU through the positions of P3 and P4 such that it meets line PQ at R. A normal N2 is drawn to face AC at U. Now PQ represents the incident ray. In the absence of the prism, the incident ray moves along the direction PQRS without any deviation. TU represents the emergent ray. The angle PQN1 made by the incident ray PQ with the normal N1 is called the angle of incidence I. The angle TUN2 made by the emergent ray TU with the normal N2 is called the angle of emergence E. Now, angle SRT is called as the angle of deviation D. The angle of deviation is the angle by which the incident ray deviates. Here, it is important to note that the total deviation of light is D is equal to D1 plus D2, where D1 is the deviation of light at the first face of the prism and D2 is the deviation of light at the second face of the prism. Now let us see what happens when the angle of incidence is slowly increased in steps of, say, 5 degrees. Let's calculate the angle of deviation D with every increase in the angle of incidence. You can see that when the angle of incidence changes, the angle of deviation also changes. Hence, we can say that the angle of deviation depends on the angle of incidence. Note that as the angle of incidence increases, the angle of deviation first decreases, reaches a minimum value, and then starts increasing again. This can be shown by plotting a graph with the angle of incidence on the x-axis and the corresponding angle of deviation on the y-axis. The least value of deviation obtained is known as the angle of minimum deviation, dm. From the graph, we can also calculate the angle of minimum deviation, dm. Let us now perform the experiment with the prism with a different refracting angle, A. You can see that the angles of deviation are different from the values obtained earlier for the same color of light. This proves that the angle of deviation depends on the angle of the prism A. If we now allow lights of different colors to be incident on the prism at the same angle of incidence, then they deviate at different angles and emerge from the prism. This proves that the angle of deviation depends on the color of light too. The reason is that the refractive index of a material is different for different colors of light. Similarly, if you allow monochromatic light to be incident on two prisms made from different materials, but with the same angle of prism A and with the same color of light, you will obtain different angles of deviation for the same angle of incidence. This proves that the angle of deviation depends on the material of the prism, meaning it depends on the refractive index of the material of the prism. Hence, the angle of deviation depends on the angle of incidence for a given color of light, the angle of the prism, the color of the light incident on the prism, the material of the prism. Let us now allow white light from a source to pass through a narrow slit and then be incident on the prism. In this manner, a very narrow beam of light is incident on the prism. We see that when this white light passes through the prism, a beautiful band of 7 colors is obtained, which is called the spectrum. The 7 colors observed in the spectrum are violet, indigo, blue, green, yellow, orange and red. This spectrum is popularly known by the acronym VIBGYOR, formed by the first letters of the names of the colors in it. Thus, white light is split into its constituent colors. Note that violet suffers the maximum deviation, while red suffers the minimum deviation. The spectrum can also be obtained when white light from the sun is incident on the prism. Sir Isaac Newton conducted an experiment in which he allowed white light from the sun to enter a darkened room through a small aperture in a window, and placed a glass prism in the path of the rays. The beam of light that emerged from the prism lit up a white screen in the colors of a rainbow. The splitting of white light into its constituent colors is called dispersion. It is important to note that the prism itself does not produce any color. Let us try to understand the actual cause. All colors of light travel with same speed in vacuum. When they enter a medium, For example, say glass, the different colors pass with different speeds. When these rays enter a prism, they slow down by different amounts and hence they are refracted through different angles. The amount of refraction is dependent on the wavelength of the light passing through the medium, and since the white light is a mixture of different wavelengths, light of different wavelengths refract by different amounts. The refractive index of a medium is found to be greater for shorter wavelengths. Therefore, glass has the greatest refractive index for violet, which has the shortest wavelength among the colors of the spectrum. Therefore, violet gets slowed down the most, and so is refracted through the largest angle. Similarly, glass has the least refractive index for red, since red has the longest wavelength among the colors of the spectrum. Thus, red light slows down the least, and so is deviated through the smallest angle. Let us now see what happens when an exactly similar prism is placed adjacent to the first. You can see that white light emerges from the second prism. Let us try to understand what exactly is happening in this situation. When only one prism was used, we obtained the spectrum of white light. However, when another prism was used adjacent to the first, the colors of the spectrum recombined to form white light, which emerged from the second prism. Note that the beam of light emerging from the second prism is parallel to the incident beam of light. Let us now understand in detail the formation of a rainbow. The formation of a rainbow can be explained by the dispersion of light by water drops in the atmosphere. A rainbow is always formed in the direction opposite to that of the sun. When light enters a water droplet, it is first refracted and dispersed into its constituent colors. It is then totally internally reflected at the water-air interface. Finally, it emerges from the water drop and reaches our eyes. Thus, we are able to observe a rainbow. It is interesting to note that a rainbow will be visible to us even on a sunny day. When we look at the sky through a water fountain or a waterfall with the sun behind us. You know that when sunlight is passed through a prism, you see a visible spectrum, which consists of mainly 7 colors, namely violet, indigo, blue, green, yellow, orange and red. Now, if you move a thermometer with a blackened bulb in the region adjacent to the red region of the visible spectrum, it records a rise in temperature. A blackened bulb has better absorption. This shows that there are invisible radiations beyond the red region, which cause the temperature to rise. These invisible radiations just beyond the red region of the visible spectrum of white light are known as thermal radiations, since they are able to produce heat. Thermal radiations are also known as infrared radiations, since they have wavelengths just beyond the red region of the visible spectrum. When the region just before the violet region of the spectrum is investigated using a solution of silver chloride, ultraviolet radiations were detected which are invisible to the human eyes. This shows that on either side of the visible spectrum, there are invisible radiations. From this, we can understand that solar radiation consists of both visible and invisible radiations. Here, the term radiation refers to emission of energy as electromagnetic waves. Here, we will study about electromagnetic radiations. Electromagnetic waves are those which do not require a medium for propagation. They can propagate in vacuum also. Sunlight is completely electromagnetic in nature. Now, let us look at some of the important properties of the electromagnetic waves. Electromagnetic waves consist of oscillating electric and magnetic fields which are mutually perpendicular to each other and also perpendicular to the direction of propagation of the wave. For example, if electromagnetic wave propagation is along the positive x-axis, then the oscillating electric field could be along the positive y-axis, while the magnetic field could be along the positive z-axis. Thus, electromagnetic waves are transverse waves. All electromagnetic waves travel at a speed of 3 × 10⁸ meters per second in vacuum. The velocity v of an electromagnetic wave is related to its wavelength lambda and frequency nu according to the relation v is equal to nu lambda. All electromagnetic waves exhibit important phenomena like reflection, refraction, interference, diffraction, and polarization. Electromagnetic waves are not affected by electric and magnetic fields. All electromagnetic waves consist of particles called photons. Therefore, electromagnetic waves possess dual nature. That is, they behave both as waves and also as particles under various circumstances, about which you will learn later. Electromagnetic spectrum is the range of wavelengths over which the electromagnetic waves extend. Let us now study the various components of the electromagnetic spectrum, both visible and invisible, in the increasing order of their wavelengths. Here, it is important to remember that the increasing order of their wavelengths will be the decreasing order of their frequencies. Electromagnetic waves are popularly known by the acronym EM waves. The complete electromagnetic spectrum in the increasing order of the wavelengths consists of gamma rays, X-rays, ultraviolet rays, visible region, infrared rays, microwaves, and radio waves. The names given to types of waves are just for convenience in describing the region of the spectrum in which they lie. It should be noted here that there is no sharp boundary between two successive regions of the electromagnetic spectrum. In fact, they overlap considerably. Let us now study the various regions in an electromagnetic spectrum, their method of production, properties, and uses. The basic source of any electromagnetic waves is an accelerating charge. Let us first look at electromagnetic radiations with the highest frequency, called gamma radiations. They are released when an excited nucleus comes to a lower energy state. Now, let us discuss some of the properties of gamma rays. Gamma rays have the highest frequency, possesses very high energy, and are extremely dangerous to living beings, since they are highly penetrating in nature. They can penetrate through thick metallic sheets, even 30 centimeters thick iron. Gamma rays have extremely short wavelengths, in the range of 0.001 angstrom to 0.1 angstrom. Some other important properties of gamma rays are that they can cause fluorescence on materials like zinc sulfide. They can penetrate through thick metallic sheets, and they are also present in the cosmic rays. Let us now discuss some of its uses. Gamma rays are useful in the field of medicine for treating cancer and also in industries to check welding. Gamma rays can be detected by using a photographic film or an ionization chamber or by using a Geiger tube. Let us now learn about X-rays. They are produced by bombarding heavy metal targets like molybdenum with high-speed electrons in a Coolidge tube, which is also called an X-ray tube. X-rays have short wavelengths in the range of 0.001 angstrom to 100 angstrom and high penetration power. They can penetrate human flesh, but not bones. X-rays are invisible to human eyes and can damage or destroy living tissues. Therefore, it is advisable to avoid unnecessary exposure to it. X-rays are used as a diagnostic tool in radiography, which is popularly known as X-ray photography, and to look at materials in industry for defects. They are also used in the treatment of certain forms of cancer. They can be detected by using a photographic film or an ionization chamber or by using a Geiger tube. Now let us learn about ultraviolet radiations, also called UV rays. They were first detected by Professor J. Ritter. They can be obtained by passing sunlight through a quartz prism, since quartz does not absorb ultraviolet light. Ordinary glass prisms can absorb ultraviolet light. They can also be obtained by using a mercury lamp with a quartz envelope. The sun is an important natural source of UV rays. However, long exposure to UV rays has harmful effects on human beings. Now, let us discuss the properties of UV rays. Have wavelengths in the range of about 6 angstrom to 4000 angstrom, and they produce fluorescence on a zinc sulfide screen. UV rays are used in a variety of applications such as LASIK, eye surgery, water purifiers to kill germs and bacteria, in fake note detectors, and so on. UV light is also useful in detecting fake gems, minerals and diamonds, and checking for the purity of ghee and eggs. UV light helps produce vitamin D in the food for plants and animals. UV rays can be detected by using photocells or by photographic films. Alternately, they can be detected by using a solution of silver chloride, which first turns violet and then black on exposure to ultraviolet radiations. Now let us learn about the visible region of the electromagnetic spectrum. This is the most familiar part of the spectrum and has wavelengths in the range of 4000 angstrom to 7000 angstrom. The atomic spectra of many elements are a source of visible light. For example, sodium has atomic spectra in the yellow region of the visible spectrum. The human eye, photocells, and photographic film can detect the visible region of the spectrum. Visible light, which is emitted or absorbed by bodies around us, provides information about the world around us. The next part of electromagnetic spectrum is occupied by infrared rays, also called IR rays. They were first detected by William Herschel. Infrared rays are sometimes referred to as thermal radiation or heat waves, since water molecules present in most materials absorb IR rays and heat up, and then heat their surroundings. They have wavelengths in the range of 7000 angstrom to 1 millimeter. Infrared radiations cannot be absorbed by rock salt prism. Infrared rays are used in various applications. Let us learn about some of them. They are used in photography at night and also in mist and fog, as they are not scattered much because of their very long wavelengths. In night photography, a film sensitive to infrared rays is used. Infrared radiations are also used to track diseases in crops by remote sensing. When a crop is diseased, its temperature changes. Infrared detectors can record such changes and give information about the diseased crop. Infrared rays are also used in the remote controls of various electronic instruments that you use today. Infrared rays are used for communication in defense, as they are not absorbed much in a medium. They are also used by doctors for therapeutic use in curing joint pains, etc. Let us now learn about microwaves, which have wavelengths in the range of 1 millimeter to 0.1 meter. Microwaves with frequency in the gigahertz range are produced by special vacuum tubes like the magnetron valve or klystron valve or gun diodes. Microwaves are used in microwave ovens to cook or heat food or liquids. Microwaves are also used in the field of communication. Since microwaves have short wavelengths, they are suitable for the radars for aircraft navigation systems. Electromagnetic waves that have wavelengths beyond 0.1 meter are known as radio waves. They can be produced by electrons oscillating in special electric circuits called LC circuits. They are produced by accelerating and decelerating charges. They generally lie in frequencies in the range of 500 kHz to 1000 MHz. They can be detected by aerials in receivers used for communication. They are mainly used in radar communication, radio and television communication, and also in cellular phone communication networks in the modern world.